Welcome back to the Explainer. So did you know that OpenTelemetry is actually the second most active cloud-native computing foundation project right now? It's literally right behind Kubernetes. Today, for all you focus learners tuning in, we are looking at this absolute master blueprint for modern software architecture. We're talking about OpenTelemetry, or OTel for short. Now look, if you've ever felt like OTel has a brutally steep learning curve, I promise you, you are definitely not alone. Our goal today is to completely demystify that curve. We're going to skip the fluff and show you exactly how to instrument your code effectively so you can truly understand what your systems are doing in production. Okay, let's take a quick look at our roadmap for today. We're going to start with the OpenTelemetry standard, then move into trace-first design. After that, we'll tackle complex architectures, look at layering your telemetry signals, and finally, we'll wrap up with schemas and AI assistance. Let's get into it.
Section 1. The OpenTelemetry standard.
Right, so in the chaotic reality of most brownfield systems, telemetry is usually just bolted on as a total afterthought. Which brings up a really valid question, and honestly one you've probably asked yourself. Why is OpenTelemetry's learning curve so often called a steep cliff? It's a real frustration. When you first adopt OTel, you're immediately hit with this dizzying array of terminology and a massively broad API surface area. It feels completely overwhelming. But what if we shift our perspective on what OTel actually is? That brings us perfectly to our definition. OpenTelemetry is an open-source standard that provides semantic conventions for exactly how telemetry is created, transmitted, and interpreted. What makes this so incredibly powerful is that OTel isn't just another tool you install. It's a universal standard. It basically acts as a structural blueprint for observability. It guarantees that telemetry becomes native to the libraries and frameworks you are already using, rather than being some proprietary bolt-on that just locks you into one specific vendor forever.
Think of it like city planning. On one side, you have pure chaos. Imagine an intersection with mismatched traffic sensors, and they're all reporting in completely different units and formats. If just one of those sensors fails, you have to rebuild your entire analytics pipeline just to read the new replacement. It's a nightmare. But on the flip side, we have a standardized approach. You have a single normalized telemetry pipeline where components can be swapped out instantly, simply because they all speak the exact same language. Basically, no more spending your weekends ripping and replacing code just because leadership decided to change the observability backend.
Okay, moving on to Section 2, Trace-First Telemetry Design. To really understand trace-first design, we have to talk about context. Context is the foundational glue here. It associates all of your telemetry signals back to a specific request, transaction, or unit of work. It propagates identity, things like trace IDs and span IDs, throughout your entire distributed system. Now, whether that's implicitly handled by your language library behind the scenes or you're explicitly injecting and extracting it over HTTP headers, context is the magic that makes the entire model function seamlessly across all your different services. Now, a super common instinct when developers first grasp the idea of context is to just go wild and create a span for every single function in their codebase. But hold on a second. Before you create a span, you really need to ask yourself two very specific questions. Otherwise, you're going to drown your system in useless noise and absolutely burn for your budget. Here's a quick little heuristic checklist for you. The two vital questions are, first, is the operation interesting? And second, is it aggregable? Let's take a database query, for example. Is it interesting? Well, yes, it's input/output bound and can have wildly variable latency. Is it aggregable? Yes, again, you can group it by query type to spot trends over time. So, boom, it earns a span. But what about a static math calculation? That's not really aggregable into any useful trend. So, no span. Keep this mental cheat sheet handy whenever you're deciding where to actually instrument your code. Let's jump into Section 3, Instrumenting Complex System Architectures.
So, we've seen the basics, but what happens when we leave the comfort zone of request response and enter highly constrained or asynchronous environments? Let's think about stream processing, like ETL jobs flowing across Kafka queues. Standard traces just don't fit that classic waterfall representation here, because the data is flowing asynchronously. The standard parent-child spans will completely break down. So what do? Well, you have to use what are called span links to connect your separated producer and consumer traces. Or, if you're dealing with event sourcing, you might have to blend your signals, maybe using histograms to track the number of stages a transaction goes through rather than trying to force the whole thing into a single massive trace.
Now, serverless environments like AWS Lambda, they present a totally different set of constraints. In serverless, your biggest enemy is cold start times and memory usage. So instead of running a heavy stateful SDK inside your actual function code, you use a stateless SDK right in the serverless runtime layer. It just emits lightweight raw events over to an extension layer. And that extension layer, which usually houses the OpenTelemetry collector, does all the heavy lifting of buffering and building out the actual spans. It is a fantastic pattern if you want to maintain absolute peak performance while still getting great telemetry. You can also add a remarkably powerful capability to your tool belt, eBPF instrumentation. This stuff is fascinating. We're talking about small, safe, incredibly low overhead programs that run directly in the Linux kernel. And the best part? They require absolutely no process restarts or recompilation of your code. Think of eBPF as the ultimate gap filler. It hooks right into the kernel, providing deep visibility, gathering metrics and traces from things like HTTP and gRPC services without adding any runtime overhead whatsoever to your user space code. It honestly feels a bit like magic when you see it working in production. Section 4. Layering your telemetry signals.
All right, now that we've captured all this rich data from our complex systems, how do we actually use it efficiently? We definitely don't want to create massive, expensive data duplication. The secret here is layering. Duplication is when you emit the exact same data to multiple backends, which, let's face it, is incredibly wasteful. Layering, on the other hand, is providing multiple views, so traces, metrics, logs, of the exact same work, all perfectly linked by that shared context we talked about earlier. Layering is exactly like using a microscope. You start with high-level traces at the service boundary as your structural glue, and then you zoom in with detailed metrics or logs only when and where you actually need them. And here is the real kicker. The OpenTelemetry collector can actually generate your metrics directly from your span data, which saves you from having to write duplicate instrumentation code.
To help you layer effectively, try using this simple 3-question framework to decide which signal to use. Question 1. Is this a high-level symptom? If it is, use metrics. They're perfect for fast, aggregated dashboards. Question 2. Is this a discrete unit of work? If so, you want to use spans to track the execution paths and measure latency. And question 3. Is this a highly specific detail? Then you want to use span events or logs to get that granular context. So, to quickly summarize, metrics are for your dashboard symptoms. Spans trace the actual execution journey. And logs provide those zoomed-in details you need for squashing the toughest bugs. Let's hit our final section, Section 5, Schemas and AI Assistance. Looking toward the future of instrumentation, we really need shared organizational agreements. First up is schema-driven telemetry. Essentially, this means defining all your telemetry conventions, your names, attributes, metadata, in a single schema file to build a shared organizational truth. Let's be real, if you adopt OTel across a large company without rules, things get messy fast. Tools like OpenTelemetry Weaver allow you to codify your conventions into a schema. This ensures your team stop reinventing field names, preventing those situations where you have 5 different slightly misspelled variations of customer ID floating around. It helps you maintain a pristine, predictable data pipeline. And having that solid schema is incredibly helpful when we start introducing AI into the mix. AI is a total game changer here, largely because large language models are heavily trained on OTel's open source patterns. But, and this is crucial, you must use a planning mode first. Please don't just ask an AI to blindly write instrumentation code. You have to feed it specifications and context, like your user stories, and then ask the agent to create a concrete plan. Once you review that plan to identify the boundaries, you generate a schema spec for its memory. You are effectively feeding it context to create a reviewable blueprint before it writes a single line of code. This is how you ensure you get truly useful telemetry, rather than just telemetry that technically compiles. Well, we have covered a tremendous amount of ground today. As we wrap up, I want to leave you with this somewhat provocative thought. If you had to completely switch your observability vendor tomorrow, would your current telemetry setup actually survive the migration? If you are heavily locked into proprietary agents, the answer is probably no. The ultimate payoff of OpenTelemetry isn't just about getting better visibility, it's about the absolute freedom and portability that comes from standardizing your architectural blueprint. When you control the telemetry standard, you control your own data. Thanks so much for joining me on this explainer today. Keep building, and I will see you next time.